Good morning, Astronomy 1020. Welcome to part 2 of our 13th lecture, where we're attempting to cover the death of stars. We've got a program today where we're going to try to talk about maybe a little white dwarf, maybe a little bit of neutron star, maybe even we'll get to black holes if we're lucky. In our last lecture, I reviewed the life cycle of a low mass, one solar mass star so that you could remember the gyrations it went through as it went from a main sequence star to a red giant. There was a few different substages of red giant, and then eventually to its death. What's up, Runsack? Today, I wanted to kind of do the same thing for a high mass star, but I'm worried that if it goes the way that Tuesday went, I'll spend the whole lecture kind of reminding you about the fusion gyrations of a high mass star. I'm kind of excited to get into their stellar remnants. Astronomers call the death of stars, the thing that's left over, they call them remnants. And our homework today from chapter 18 is about remnants. It's about neutron stars and white dwarfs and black holes. So I might save the review of the high mass star for next Tuesday, and I might try to get into some of the wacky fun that is the death of stars. And you guys should find that, as my old professor used to say, not uninteresting, okay? So,
question for you, Mr. Britton.
Yeah, Chris, hit me.
When is our last day for when our exam hits, anyway, I meant?
So the way things are supposed to go is next week we have our last two lectures, lecture on Tuesday, lecture on Thursday. I haven't decided which lab I want to do on Tuesday, and I haven't decided which homework I want to do on Thursday. And then there's the question of the final itself. One student in one of my classes advocated for somehow not having a final. And I have done this before where I've allowed students the option to basically substitute their midterm exam for their final. So I'm just going to grab the column for midterm exam and I'm going to put it into your final as well. And it turns out that most people score close to their midterm exam on their final. Sometimes a little higher, sometimes a little lower, but usually it's only a few points at best. Riordan seems to be excited. It's nice to hear from you, Riordan. I finally have something that you want to talk about. I'm thinking about it, Riordan. You know, I don't like to do these kinds of games. A 10-point holiday bonus. Now you're squeezing me. Now you're squeezing me. That's a little difficult to do. That makes me uncomfortable or nervous. I have to think about how to explain why. But let's just put the holiday bonus aside for a second, okay? I didn't get a holiday bonus, you know. No one's given me a holiday bonus. I wish they would. Anyways, putting that aside, if I were to make that an option, how many of you would take that option?
I definitely would.
You definitely would. Okay. So you guys would rather just have your midterm grade be your final grade and not have to go through that ordeal. That's what you're saying? One of the reasons why I've been trying to justify this in my head in a couple of different ways. And one of the ways I'm trying to justify it is we are in an extraordinary kind of situation here. And I asked some of my students yesterday, I kind of broke the fourth wall for a second, and I'll do the same with you guys. How many of you are taking multiple classes, just not just my class?
Yep.
Wow. So a whole bunch of you trolls in the background are too. And I've got to imagine some of you, many of you have jobs too, like Chris was there holding the gates back at Walmart, right? And Stacy's working, and Kaitlyn's, you still working your bank, Kaitlyn?
A full 40 hours a week, 9 hours a day.
Holy smokes, kid. You must have no free time. That's crazy.
Nope, none.
So at finals, I remember it's very stressful because now all this crap is due, right? You got all kinds of papers due. And I asked students how they were doing, and some of them were like, to be honest, I'm kind of struggling in some of my other classes. So I think that anything I can do to kind of open up some space for you guys would probably be pretty welcome at this point, right? Especially because you guys have been doing this whole semester from your little bedrooms there, just like I've been teaching from my loft downtown. And has that been hard? Do you guys feel like it's been harder working from your home than it would have been in school? That's something I'm curious about.
Much harder.
I'm trying to feel like how I've actually kind of had fun with my little board, and I brought all my props here. I certainly like being able to go get coffee in the kitchen and stuff. That's kind of cute. But I don't know, it is kind of nice to have a space where all of your home stuff is separated from it, you know? So, so in any ways, my point is I'm thinking I could justify skipping the final and replacing the final with your midterm exam grade. I think that would be ethical under the circumstances. And it sounds like you guys would be all about it. Is there anyone out there in the troll sector or anyone at all who thinks they would rather do the final than, let me show non-video participants for a second. Anyone out there in the troll zone who thinks they would prefer to try the final rather than double their midterm? I don't see anyone saying, looks like all the trolls are saying same thing you guys are, so. Okay, Devin's happy with not taking it. Okay, you know what? Then I think a class, hold on, let me hide the trolls again, because, oops, sorry. Hide the trolls. I wish they made the button easier to get to. I think above all things, yeah, Riordan, I could do that. I think I have to give, if someone wants to take the final, this is the thing, I would just like it to be the same for everyone because that's like so much less crazy on me, but I don't think I can get that. I think I have to give you guys the option, but you can't do both. You can't double your midterm and take the final because then that hurts me, okay? So you have to choose one or the other. You take the final and you get what you get, or you double your midterm grade. It sounds like I haven't heard anyone say I am dying to take a multi-hour final exam. And, you know, anyways. Hey, guys, I'm just going to go adjust the heat. I'm wearing my velvet jacket for you guys today, and it's a little hot in here. Okay, so if we are not going to have a final exam, then I probably will try to do a lab, and I will do a homework next week rather than practice problems for the exam. Or maybe I'll make our final problem set problems that were going to be on the exam, and we'll do a couple of them together, and you guys will turn that in for another homework grade. So that's another possibility of what I might do. And then it's kind of like we did the problems together or something. So, okay, one last pitch that I want to make, more administration before I get to my lecture today. I noticed when I was looking through old student evaluations that with the chaos of last spring and COVID, hardly anybody went to rate and evaluate the class. I think in one of my classes, one person did an evaluation, and it was very confusing because all of their answers were, I don't know, I don't know, I don't know. So it was just totally bizarre. So thank you, Cameron. I appreciate that. I certainly appreciate it around this time when I'm going up for promotion. So yes, exactly. Break the scale. Anyways, I don't know if you guys know how to do that online. I always used to like the paper versions because I kind of forced people to do it. But if you are unfamiliar with how to do a student rating of instruction, I believe you go to your My CCRI. Let's see if I can find this here. And, oh geez, it's gonna make me sign in again. Okay, sorry. This is all taking a little more time than I wanted to. Okay, I don't know how you guys do it. You probably have a For Students tab, but I have a For Faculty tab, and my student ratings of instruction, SRIs, are down here. So you guys probably have a student rating of instruction in a box like this. I'm not familiar with how it looks on the student side because I've never been a student here.
It's like a little, I think, red flag on your personal schedule that you click.
Oh, thank you, Christopher, for that intel. Okay, so some of you guys know how to do that.
Not every teacher has it available. That's why you might not see it for everyone.
It may be that I need to activate some kind of flag to make them digital. So if you guys don't see it from me, please inform me of that. Obviously I'm teaching now, or I should be teaching now, so I can't do it, but I'll try to remember to look at the end of class.
I saw yours on there, Professor.
Say that?
I saw yours on there. I was able to do it.
Oh, killer. Okay, great. Great. Okay, guys, let's talk science because that's more fun than administrative stuff. Do you guys remember what do we get left over when a lower mass star like the sun, a one solar mass star dies? What products are left behind?
I got you. There's the small, not small, but like the tiny carbon center,
Yes.
and then you have the leftover gases that's just spreading out.
And what do we call those gases that we looked at last time? Hey guys, boy, I'm just really weird today. I lost my damn marker. That's fine. I'll just take a fresh one. I wonder what the hell I did with that thing. It's been a confusing couple of days. Maybe this is it. No. All right. Okay. This one? No. All right. I got a freshie. So for a low mass star, and it turns out that intermediate mass stars also suffer the same fate. And intermediate mass stars, the end state, so let's call this the end state of stellar evolution, or let's just not use any fancy terms today. Let's just call it the end state of stars. Is to end up with two products. There is the gases, which I think that was a Runsack talking to me, which we call a planetary nebula. And you guys will remember that I showed you some lovely pictures of planetary nebula, some of my most favorite objects to look at through a telescope. And the husk, as a Runsack calls it, the carbon cinder, the ash of carbon, which is the so-called white dwarf. And although it is somewhat of a simplified, cheesy illustration, I think a nice couple of pictures to look at from my stellar death lecture. This, of course, this nebula that you're seeing here is the legendary Eta Carina Nebula, which has all kinds of things going on in it that we talked about over the course of this semester. You can see stars, you can see dust clouds and giant molecular clouds. These are all giant molecular clouds where stars form. And I believe one of these bright dots, I think the one here right in the center, actually turns out to be, if you zoom in on it and adjust your contrast, it's the legendary Eta Carina star, which is a low mass star in the throes of expelling its outer envelope of gas. And this will eventually turn into a planetary nebula. Probably once it expands a bit, I'm guessing it's going to end up looking like the Ant Nebula or the Twin Jet Nebula, one of these hourglass-like shapes. And you can see the two lobes developing as the star is expanding. We're kind of catching it a little earlier in the program. But the cartoon picture, of course, would be, well, something like this. So this will be the cinder left behind. This is the white dwarf. And these gases out here will become the planetary nebula. Suppose I just asked you guys a couple of thought questions to test you here, since I may not get another chance to test you. What would the composition of the gas in the planetary nebula be made out of? This is supposed to be a simple question, but you have to think about it for a second. What would the gases that make up the planetary nebula be comprised of?
Helium or hydrogen?
Which?
I'm going to go out on a limb and I'm going to say helium.
It turns out to be both.
Oh.
The point that I was trying to make here, Kaitlyn, and I might have asked that question in a somewhat awkward way, but if you look at these stages of a star's life, remember that the gases that make up the planetary nebula were once the outer envelope of the star, meaning its convection zone and its radiation zone and its photosphere. So I was hoping that you would reason as such. Well, these gases were once a part of the outer layers of the star, and I know what the composition of all stars is. This is something I would have tested you on. What are the composition of all stars? They're similar to the sun.
Helium, hydrogen, heavy metals.
What percentages?
Oh, 70, 20 something, and then 1% metals.
I think it's 2 heavy metals.
Sorry, say that, background person.
I said I think it's 2% heavy metals.
That's right. It's 70% hydrogen, 28% helium. So Kaitlyn, you would have been better off saying hydrogen than helium, okay? And then as someone pointed out in the background, 2% metals. And I like your astronomy jargon there. That's kind of nice. It turns out that pretty much all stars that we've ever observed in the universe basically have this composition. Now, I'm lying to you just a little bit. Sometimes I like to tell you lies because it's easier than telling you the truth. And stars do have slightly variable layers of metals. People make a big deal about this in stellar astronomy. They actually try to test and measure the so-called metallicity of stars. However, to a first approximation, this is correct because stars who vary in their metallicities will vary from like 1.7% metals to 2.2% metals. So it's very, very close to 2 always. Runsack.
Is that 2% metal? Is that the thing that becomes the carbon center after the low mass star dies?
Yes, and that's, Runsack, you're anticipating my thing here. I was trying to get you guys to remember that stars have this composition and the planetary nebulae have these composition, but because the white dwarf is the center nugget that's been, actually, Runsack, let me even elaborate on this. In the beginning, the universe created light in the form of the Big Bang. And the Big Bang was an explosion of light and matter that, I don't know, somehow came out of nothingness, as weird as that sounds. And we know a lot about the Big Bang because the leftover glow or radiation permeates all around us in space. We can see the background light from the Big Bang using radio telescopes. And we study the intricacies to learn about the composition of the early universe. We know that the early universe was 100% hydrogen and helium with no metals. And what that means is all of those 2% metals came from subsequent star formation fusing hydrogen to helium, helium to carbon, and then in the case of higher mass stars, carbon to all the way to iron and other things. So yes, gold included, Cameron, indeed. And what about protactinium? Ever think about protactinium? Okay, anyways, the white dwarfs are an example of pure 2% metals because mostly white dwarfs are made out of carbon. In reality, some white dwarfs have an oxygen-helium mixture as well. There's some oxygen in white dwarfs as well, but I don't want to overcomplicate things. I want to tell you something simple that's close to the truth. And that's most white dwarfs are made of carbon. Remember that carbon is the leftover byproduct of red giant fusion. This carbon comes from the so-called triple alpha process, which is what those pulsating helium fusing stars are doing when they take 3 helium nuclei and bash them together to make 1 carbon and 2 gamma rays. Hey, I've got a thought question here. This might be a challenge question, but I'm not afraid to challenge you. Each reaction of the triple alpha process produces 2 gamma rays. How does that compare to the efficiency of energy production in the proton-proton chain? I'm asking you kind of an adult science question here, so put on your big boy pants. If each reaction of the triple alpha process produces 2 gamma rays, how does that compare with the energy efficiency of the proton-proton chain?
Is it double the efficiency? If I remember correctly, the first one makes 1 gamma ray, right?
Ah, but there are 2 branches, Runsack. Here, I'd like to borrow from good old Wikipedia. Just has some wonderful stuff. I love Wikipedia. I think one of the greatest gifts to the modern world is the fact that you can just go on the internet and learn anything for free is wild, and learn it in quite some detail. Look at this beautiful illustration of the proton-proton chain that someone did and uploaded to Wikipedia. You can see the first branch of the reaction, 2 hydrogens slammed together to make deuterium. Deuterium slams with another hydrogen. There's your 1 gamma ray, a Runsack. But remember, you need 2 helium-3 nuclei, 2 helium-3 isotopes to slam together to eventually create your alpha particle, your helium-4 nucleus. And that means for each reaction, there are 2 branches and you produce 2 gamma rays. So, Runsack, how does the energy efficiency of the triple alpha process compare to the energy efficiency of the proton-proton chain?
It's equally efficient.
Ah. And now, Runsack, here's where I'm going to pull the rug out from underneath your feet and say your first answer was more correct than your second answer. In fact, it's less efficient. Actually, no, your first answer was way more wrong. Sorry. The triple alpha process is way less efficient, despite the fact that it produces 2 gamma rays. Now, if you're scratching your head, then I've got your attention. Hear me on this, okay? Do you remember what a nucleon is? What's a nucleon?
I think it's 1 proton, 1 neutron.
It is a proton or a neutron.
Okay.
Okay. How many nucleons do I need to put together to make my 2 gamma rays in the proton-proton chain?
Two.
One of my questions for the proton-proton, one of the questions I was going to ask you on the final exam is, what is the overall net reaction of the proton-proton chain? What's the net reaction in the proton? Boy, it's a damn good thing you guys ain't taking that final, huh? I'd have you guys tripped up 6 ways to Sunday. Let's look at our slides. Let's do some membrane. We need to do some good membrane here. What is the overall net reaction of the proton-proton chain? Hint, look for the pink box. Come on.
Wait, I'm sorry. Can you repeat the question one more time?
Yeah. What is the net reaction, the overall input and output of the proton-proton chain? In other words, Kaitlyn, I'm not asking you to describe the 3 steps. I'm asking you to describe what goes into the cake and what comes out of the cake. You know, like first you put in flour, salt, sugar, and then the other end comes out a birthday cake. I want to know what ingredients go in. Basically, I'm asking you to summarize this.
Oh, okay. So 4 protons go in.
Yes.
And what is that? 2 neutrinos and then 2 positrons.
Normally people don't talk about this, so forget about that for a second. Focus on
2 gamma rays.
2 gamma rays plus this doodad. What is this doodad called?
Oh, protons and neutrons.
You have to take it holistically. What is this particle? This is a...
Oh, an atom.
What atom?
Oh,
Jesus.
I don't know.
It's mother.
Oh, is that hydrogen? Helium.
I was hoping you guys would know what the composition of the second. I'm not asking you about molybdenum or protactinium or californicium, or I'm asking you about helium, the second most abundant element in the universe. I was hoping, okay. You will never forget this, Kaitlyn, or I will scribble on your face with my magic marker here. A helium nucleus, oh, I can't scribble on your face. That's terrible. A helium nucleus is 2 protons and 2 neutrons. They call it an alpha particle, okay? An alpha particle.
Oh, okay.
Okay, geez, wow. We really got lost in missing the point here. How many nucleons go into making the proton-proton chain? It's 4 nucleons, 4 protons. Because it's 4 hydrogens make 1 helium plus 2 gamma rays. Now, what about the triple alpha process? How many nucleons go into making those 2 gamma rays? Triple alpha, by the way, Kaitlyn and friends, means 3 alpha particles, right? 3 helium nuclei. I assume that when I talk about this stuff, you guys know what I mean, but I'm starting to question that.
6 nucleons?
Not 6. How many nucleons are, let's try a simpler question, Runsack. How many nucleons are in 1 helium nucleus?
2.
Oh my God.
4.
Where's my shotgun? I want to just go blow my
4.
here, okay? Listen, what is a nucleon? A nucleon is a neutron or a proton. How many nucleons are in a helium nucleus?
I see 4.
4. So how many nucleons go into the triple alpha process?
4 times 3, 12.
And how many gamma rays do you get out?
2.
The point that I'm trying to make to you, Runsack, is this is actually not the same efficiency because it depends upon how much energy you get out per unit mass. Remember that fusion proceeds by the legendary equation E equals mc squared. During that fusion reaction, we are shaving a little bit off of the protons and the neutrons, and we're turning that mass into energy. You're getting the same amount of energy out, but this was only 2 gamma rays for every 4 nucleons. This gives you gamma rays for every 12 nucleons. So each time you do the reaction, you use up more of the mass of the star. The meaning of this is that the star cannot fuse helium to carbon for the same length of time that it fuses hydrogen into helium. How long will our sun fuse hydrogen into helium for? What's its main sequence lifetime?
Like 8-9 billion years.
10 billion years is usually the go-to answer.
Whatever.
But all right, Christopher, you weren't wrong. Do you think that a red giant can fuse helium to carbon for 10 billion years?
No.
No, because it doesn't have the same efficiency per reaction. Take a guess. How long? There's no reason you should know the answer to this, but guess for fun, Christopher, since your intuition has been good. How long do you think the sun can survive doing fusion as a red giant, fusing helium to carbon?
I think it's like 1 million years or something.
1 million is too short compared to 10 billion. I mean,
Okay.
here you've got 2 gamma rays for every 4 nucleons, right? This is 12. It ends up being like maybe 1 billion years is what you'd get. This is lame and it's not this simple, but this is like 1/3 of the efficient. You have to use 3 times more mass for the same amount of energy. So you're chopping it by 1/3 or maybe by even 1/5, you know? It's close to 1 billion years. Yeah. What happens when the helium fuses to carbon? Well, remember that a low mass star will never be able to get hot enough to fuse carbon. And that's when you get some wacky things left over. Let's talk. We talked about the planetary nebula a little bit. Here's what I have to say about planetary nebulas. Pretty. That's it. That's all I've got to say about planetary nebulas. They're pretty, okay? Now, they are returning enriched gas back to the galaxy, which can later form new stars from more enriched metals, but maybe I'll get on the star gas star cycle next week. Let's talk white dwarfs. They're weirder than you think they are. Okay, some notes about our friend, the white dwarf. The white dwarf is the leftover carbon, I guess you could call it the nucleus, but let's call it the core. The leftover carbon core of a low mass star. In fact, technically speaking, it is not a star. What is our working definition of star in this class? I had a clever and very short definition of star that we used in this class.
A glowing hot body.
No, a light bulb is a glowing hot body. It's not a star.
Plasma ball.
The Spencer's gift toy. No. A lightning bolt is a plasma. Well, it's not a ball. Okay, hold on.
It's light.
This is a plasma ball, a Runsack. That's plasma. It's in a ball. That's not good enough to be the definition of a star. You're missing the effing point.
Oh, a ball of fusion.
That's right. Star
Yeah.
means ball with fusion, okay? Ball with fusion is definition of star. And in that sense, a white dwarf is not a real star because there's no fusion. In fact, all that star is degenerate carbon. It's held together by something called electron degeneracy pressure. This is kind of an advanced topic, but we have to talk about it. In other words, it is a ball of degenerate carbon. Okay, we got to slow our roll here for a second. What the hell do I mean by degenerate? That is a charged term to a physical scientist. Does anyone remember what degeneracy pressure means? No. Maybe I could show you. Let's go to those physics apps that I've got. Sorry, I'm dying a little bit. No! Okay, all right, sorry. What? Why can't I run this thing? Do you remember how they said they were going to stop supporting Flash at some point? I think I'm running up against that. Oh no. Oh no. This is terrible. Okay. We'll have to try this a different way. Huh. I wonder what's going on there. I don't suppose we've got any tech gurus in the house. I'm just going to keep clicking it, hoping that something different will happen. But let me try opening it with Internet Explorer. That might be kind of weird. Open with More apps. Let's see if this works. I'll trick it. Can I trick you? Allow. Haha. Fuck. Okay. All right. I thought I could outfox this thing. I'm going to need to talk to a tech guru. Darn. Okay, all right. I can't lose the thread here. A degenerate gas is different from an ideal gas in the packaging of the particles. In a normal gas, there is a large interparticle spacing between the atoms in the gas. So let's draw, in fact, this might be more helpful because you guys can draw the particles. Okay, so let me get my stool. In a normal gas, atoms bounce around with a great distance separating the particles compared to their diameters. So in this normal gas, we have a bunch of particles that are kind of moving in different directions, and they're all kind of traveling in some random direction, okay? But the interparticle spacing is great. In a degenerate gas, you uncomfortably squeeze the atoms together such that the distance between the particles becomes comparable, or in some cases even less than the interparticle separation. In other words, you've squeezed your particles so tightly that they are piggybacked on top of each other, and they're pressing up against one another in defiance, or in almost defiance, of the Pauli exclusion principle. It's a highly compressed gas. Now, the physical difference between them, and the reason why it matters for stars, is that normal gases obey the ideal gas law, where pressure is related functionally to temperature. Unfortunately, I couldn't use my physics Java app with you, but remember, if I heat up a gas, the particles move faster and you get more pressure on the walls of the container. In a degenerate gas, you've packed the particles so tightly that their temperature kind of becomes like the buzzing of bees in a swarm of bees. They're all doing a little jiggly bee dance. And unfortunately, in a degenerate gas, or maybe fortunately for the survival of stars, pressure does not depend upon temperature, but pressure instead is related to quantum mechanics. Pressure is determined by the so-called Pauli exclusion principle. Principle. Sorry. Did I do that right? Wow, my spelling sucks. The Pauli exclusion principle should be kind of a crazy concept, but every chemistry student has to learn about it when they learn that electrons can have spin up or spin down and cannot occupy the same quantum state. Whatever. This degeneracy supports the white dwarf from collapse, but it also means that the white dwarf is highly compact. Maybe it's time for a cartoon or a cartoon illustration. Oh, stellar death. Here's a little model. This is what a white dwarf would look like. In fact, believe it or not, students, we have images of a white dwarf. This happens to be an artist illustration, but we actually have bona fide pictures of a white dwarf, and I'll show that to you in just a moment. A typical white dwarf consists of degenerate carbon, maybe surrounded by a very thin 50-kilometer thick layer of normal gas. I want you guys to check out the radius, 6,000 kilometers. Here's where we get to the good stuff, okay? I need to erase this. Any objections? Okay, this is the important part of today's notes. Typical values for a white dwarf. The mass of a white dwarf is typically close to 1 solar mass of material. The typical radius of a white dwarf is close to 1 Earth radius. How does that make you feel? How does that make you feel, Runsack?
How does what make me feel? Sorry, my buddy was distracting me.
Okay, insignificant. You know what? You're special, Cameron. You matter. Okay, listen. The whole point here is that at this point, you're supposed to say, holy effing shoot, okay? That's crazy that you would pack a mass equivalent to that of our sun into a sphere that has the volume of Earth. That would be like smushing the sun into the planet Earth. That's weird. That's wacky. That's wild. And it's almost entirely pure, let's say hot. Degenerate carbon. Hey guys, what's carbon? What's made of carbon? What is pure carbon anyways? I can't remember. When I say carbon, you think what?
Life.
Life is carbon-based, but DNA has more than just carbon, my friend, right? Deoxycarbon or ribonucleic acid, DNA, could be considered the key signature of life. And as I'd like to show you in this excellent picture from Wikipedia, you can see that, come on, baby. If you look at the atomic structure of DNA, it consists of, yes, carbon atoms, but also nitrogen, oxygen, hydrogen, and phosphorus. We refer to it as carbon-based life because carbon forms the backbone, excuse me, of these molecular chains. But I'm talking pure carbon, a Runsack, not carbon with a bunch of stuff stuck to it. What are the so-called allotropes of carbon? Here's something that's close to pure carbon. What is this?
Is that coal?
Yeah, it's a type of coal called anthracite. It's very shiny. Anthracite is highly compressed coal.
You got for Christmas?
I'm giving this for Christmas. And I'm giving it to all of you. All right. All right, listen. Coal is not 100% carbon. It's like 96% or something. This shiny black coal.
Diamond.
Diamond is one of the allotropes. What's the other one?
Graphite.
Very good. Allotropes of carbon. Typically, bear with me here. Oh, you guys are in the way of my diagrams. Allotropes are different ways. Oh, wow, there's a sample of glassy carbon. That's beautiful. That's just beautiful. Okay, let's look at the structure of diamond versus coal. coal, I'm sorry, not diamond versus coal, diamond versus graphite. Pardon me, students. Diamond has the atoms of carbon arranged in a tetrahedron shape. In graphite, they're arranged in hexagonal sheets of hexagonal rings. Typically, the density of carbon, if we go to the periodic table of the elements, Sergeant Welsh, our good old standby for everything that we need to know chemistry-wise. Let's find that high resolution one. Is this? No, that's not the big boy. Where's the big boy? Yeah, 3,000 pixels. Give me all that you got. Nope. Hold on, I need to minimize you guys for a second. Images, tools, size, large only, click. I need to wait for this to clear and then open a new tab. That's how we do it. Okay. According to this graph here, or according to this periodic table, at standard temperature and pressure, the density of carbon, whether it is diamond or whether it is graphite, is 2.3 grams per cubic centimeter. Here's what I want you guys to do with me today. Remember I said I wanted to do some math? Let us calculate the density of a white dwarf. Do you guys know the formula for density? I like to use this symbol delta for density. That's my preference. How do we define density? No? Runsack.
I think it's mass over volume.
Very good. And if I were to tell you, Runsack, that the white dwarf is in the form of a sphere, do you know what the volume of a sphere is?
One-third pi r squared.
It can't be r squared because square is an area. Try again. You're close.
This is just r.
R is a linear dimension. That's centimeters. It's 4/3 pi r squared. Wow. 4/3 pi r cubed, right? If I substitute that in for volume, I get this important formula for the density of a sphere. The density of a sphere is 3 times the mass divided by 4 times pi times r cubed. Where I took the 4/3, remember that the bottom of the bottom goes up to the top. So I flipped the 3 up to the top. Take a moment to copy that down. Calculators out. I feel a math storm coming on. All right. I'd like to see that ready to go, Kaitlyn. Okay. Let us first deal with the issue of units. Our goal is to find the density of a so-called white dwarf in units of grams per cubic centimeter. How should I go about getting my mass and radius into the proper units? Kaitlyn, you want to talk to me? No. Yes, you do. You're dying to talk to me. You just don't know it yet.
I guess. You love choosing me for math problems, don't you?
Well, I've only got 1, 2, 3, 4, 5 humans to choose from, and you happen to be all the way on the left. So, Kaitlyn, do you know what the? Oh shoot! Whoa! How did you just ended up on the right? How did you do that? That's great. Did you do that by like clicking that on and off? Oh,
No, I
weird.
didn't do anything.
Somehow, right when I said that, you suddenly shifted all the way to the right. So, okay, that was funny. I thought you did that intentionally. What is the mass of the sun?
Oh, I don't remember.
Does anyone?
Probably not.
You know, most of my students have it memorized by the end of the semester.
I'm not a memorizer.
I thought you guys were good. It's 2 times 10 to the 30 kilograms. All right, fine. Okay, but this I expect you to be able to do. Kate, my point is I need to get this into grams. How do I do that?
Fucking hate conversions.
Oh, you're so good at them though.
That's false. I don't know, man. I
Come
gotta.
on, come on, just play the game with me. You don't have to do a final exam, but you do have to do a little something.
Yep, I'm pulling it up.
Are you getting your formula sheet out?
Yeah, that's what I'm doing. I'm so sorry.
I should give you guys the good formula sheet, the one that has all the formulas. I wonder if I have that handy.
I would appreciate that.
Yeah.
Okay, so what was it again? We want it in grams and it's kilograms?
That's right.
Okay.
There's a third formula sheet, but I have the second one handy, so I'll try to send that to you guys via
Oh my
chat.
god, it's not even on here.
Hold on, there's conversions on all formula sheets. Where's the chat? There's the chat. I just sent the class exam 2 formula sheet. Okay, we have to convert, Kaitlyn. Kaitlyn, you might not even need to look it up. Just use your knowledge of science. What units
I
do you
have
want?
no knowledge of science. It's 1,000 to 1.
For what units?
1,000 grams to 1 kilogram.
It sounds like you do have some knowledge of science. Because
Google has knowledge of science.
So what's my power going to be now? 2 times 10 to what power?
Oh, to the 3,000.
Wait, not 3,000. Add the zeros. You got 30 zeros and you got 3 zeros, right?
33.
Yeah, you just add 3 more zeros. Okay. All right. Runsack, the radius of Earth is 6,400 kilometers. Can you help me get that into centimeters, buddy? Are you hiding from me now, Kaitlyn? Kaitlyn's hiding now.
You bullied her. It's fine. I don't. Is there a kilometers to centimeters conversion on the sheet?
No, I have it in my head, but I'm not necessarily going to share it with you.
Okay, let's do it all out then. 6,400 km x bar. Km bottom, meters top. And that's 1 to 1,000.
Okay.
And meters to centimeters. Meters at the bottom, centimeters at the top. And that's 1 to 1,000 as well.
No.
1 to 100.
Yeah, right. This is a meter stick. There's 100 centimeters. You do that in your head?
6,400 times 1,000 times 100. I 64 million.
6.4. 6.4.
6.4 million.
No,
centimeters.
times 10 to what?
To the 7.
Count better.
1, 2, 3, 4, 5, 6, 7, 8.
Yeah.
8, 8, 8.
Removing the 4 gets treated like a 0, right?
Mhm.
Okay. Now we're ready to calculate the density of a sphere. Here we go. The density is 3 times the mass, 2 times 10 to the 33 kilogram. I'm sorry, whoa, grams, divided by 4 times pi times 6.4 times 10 to the 8 centimeters cubed. What you get? Damn it, I turned Kaitlyn into a troll.
Does 1.8 million sound correct?
It does. Let's just make it approximately 2 million. What are the units?
Grams per cubic square.
Grams per cubic squared doesn't make no sense.
Grams per cubic centimeter.
That's right. Now, guys, I'm worried that you all might have been a little lost in the sauce here. You were so busy tripping up over your conversions that y'all might have missed my point. Does anyone know what my point is before I tell you what my point is? Yeah, Runsack.
It's incredibly dense, the white dwarf.
Normally, pure carbon, a Runsack, usually takes 2 forms on planet Earth. Pure carbon can take the form of graphite or diamond. If you had to take a guess, what do you suppose the interior composition of a white dwarf is more like? Is it more like carbon or is it more like graphite or is it more like diamond? Let's see what Mr. Chat says. Cameron says diamond. False. Both of these allotropes have a density of 2.3 grams per cubic centimeter. A white dwarf isn't nothing like either one of these things. Imagine taking a hammer and bashing all these atoms and jamming them together into a tiny little spot. These atoms have wide spacing between the particles, a generous 0.15 nanometers. That might as well be a football field to a tennis ball. Now you've smushed all of your atoms into a spherical box. And that white dwarf ain't nothing like your pappy's carbon. This is some wacky carbon, some degenerate carbon, which has been squeezed uncomfortably beyond the limit of what it wants to be. Those atoms are packed so tightly together that they more appropriately resemble a nest of bees than they do any typical matter from your everyday life. At 2 million grams per cubic centimeter, I mean, how big is a cubic centimeter? I think I've got a mahjong set here. Yeah. Here's a dice from a mahjong set. I'd say that was pretty darn tootin' close to a cubic centimeter. How many kilograms would this be worth if it was a white dwarf?
We can't see you, by the way. It's still showing a thing.
Then you missed my totally dope mahjong set. Check this shit out. I'm into games. Old games, weird games. This is a dice from a mahjong set. I'm guessing this is close to a cubic centimeter. Wow. Am I good or am I good? That's a centimeter across, right? This is a cubic centimeter. It's about the size, a cubic centimeter is pretty close to the size of your pinky fingernail, or my pinky fingernail anyways, right? Your fingernail is about a centimeter. How many kilograms would this be if it was pure degenerate white dwarf carbon? How many grams would it be?
2 million.
So how many kilograms would that be? How many grams per kilogram?
1,000.
So
So what is that?
that's 2 metric tons. I drive a big old crazy van. I carry around telescopes and band gear and stuff. So I got a band van. My Ford E150 gnarly van is a 1-ton van. This much of white dwarf would be equivalent to the weight of 2 vans. 2 of my Ford E150 vans would be compressed into this. That's how stupidly dense a white dwarf is. I couldn't pick this up. If this was a block of white dwarf, I couldn't even lift it. Its gravity would be quite strong. All right, I don't want to mess up my mahjong set, so. Y'all get my point? My point is that white dwarfs are wiggity, wiggity whack. They're not normal. They're extraordinary. Do you think these things, what's the typical temperature of a white dwarf? Let's talk some other stellar aspects. Can I erase this? I'm going to erase this. You know what? I have Runsack. This class is now no longer Astronomy 1020. This is you and me hanging out. And you and me are going to be talking about stuff, okay? Because everyone else has abandoned the fort. And that's fine. I guess I get paid either way, right? So
I got a question, Professor.
yeah.
If it's that dense and heavy, wouldn't it have the gravitational force to pull the gases back together?
I'm
You know
sorry.
what I'm saying?
Hold on. There was a little background noise. Would it have the gravitational force to what?
To pull the gases back together.
What do you mean by? I guess I don't understand what you mean by pull the gases back together, because I'm thinking the gases are pulled together. This thing is full of all of these degenerate carbon atoms, right? Like, it would take me a long time to shade this whole thing in with BBs, but aren't the gases already together, Runsack?
I mean, like the nebula that's flying away.
No, because this has an equivalent of the mass of the sun. Do you remember what the typical radius of a red giant is? The typical radius of a red giant, a Runsack, is 100 solar radii, up to 1,000, somewhere between 100 to maybe 1,000 solar radii. So pretty much that's the equivalent of having the sun be a point particle, and those gases are pushing off somewhere around 1 AU. Okay? Do you see what I mean? If there was some gas 1 astronomical unit away from the sun, it would feel gravity from the sun, but remember that gas is being ejected by the natural process of puffing out. When the star dies, the hydrogen shell fusion is blowing it out. It's feeling more of a repulsive force from the photon pressure pushing the gas. In other words, it's feeling more of a repulsive force. That's why it's expanding. The gravity is certainly dense if you get close to it, Runsack. But as you get farther and farther away from the star, it kind of acts like the sun. Do you know what I mean? Like, for instance, let's say you just magically transformed our sun into a white dwarf. The orbit of Earth would not be affected because it would continue to orbit as if the mass was concentrated at a point particle. However, Runsack, if you got very, very close to the white dwarf, like if you were closer than the planet Mercury, your orbit might start to deviate a little bit. Typically, the escape velocity of a white dwarf is approximately only 2% of the speed of light. Does that make this a relativistic object, to Runsack? Does special or general relativity come into play here? What's our cutoff for the relativistic regime? What fraction of the speed of light do you have to be at? You guys can't remember that, or you can't remember that probably. It's 20% the speed of light. This is non-relativistic. Typically the temperature, well, why don't you tell me the temperature? Let's, the zones of white dwarfs are comparable to O-type stars, like Sirius B. Based on this graph, Runsack, what would you say the temperature of the star is?
So like, wait, the zoom mean is covering the number. Okay, there you go. About like 28.
Yeah, we'll just say,
28,000.
we'll keep it simple. We'll make it 30,000, okay? Okay. Remember that these were once the nuclei of stars. They're now exposed to space. So the temperatures can be around 30,000 Kelvin, but they cool over time due to radiation loss. Would you expect the luminosities of these things to be high or low? Yes. Why? The Stefan-Boltzmann law tells us that the luminosity goes as r squared t to the fourth. Sure, they might be hot, but their radii are so tiny that they end up being quite dim. Typical values being 10 to the minus 4 or 10 to the minus 5 solar luminosities. Did I do that right? Okay, well, let's do 10 to the minus 3. Sorry. I was a little too low in my estimate there. Because they put out only a fraction of the sun's light, they can be extremely difficult to see. However, we are lucky enough to have a picture of a white dwarf. The bright star Sirius at the foot of Orion famously is a binary star in which one of the companions is a white dwarf. Now, Sirius is an A-type star, so it should be very difficult to make out the white dwarf. So here's a picture of the brightest star in the sky. This is just to help you guys orient yourself. You can see Orion here, the stars in the belt, right? And if you want to find Sirius, the brightest star in the sky, you look for Orion. Orion usually moves this way across the sky. And then you look back from his back foot, and there you'll see Sirius. On the sky, Sirius just looks like one bright star. But we have famously determined that it is a binary star. And here's an actual real-life photograph of the star in which they managed to resolve the white dwarf companion. So this is a main sequence star, spectral type A, and this is a white dwarf, Sirius B. And they're in orbit around each other. They're an example of a visual binary. Look at how much dimmer the white dwarf is compared to Sirius A. Now, in the case of Sirius A and B, they have a significant separation, so there's not too much of an issue here. But remember, the mass of Sirius A might be 3 solar mass units, right? The mass of Sirius A could be as little as a half a solar mass. I can't remember what its actual mass is. I think it's maybe a half of a sun's mass, something like that. Based on these two numbers, both of these have not exactly the same amounts of gravity, but they're similar. How far in between Sirius A and Sirius B would you have to go before the two stars balanced in a tug of war of gravity? Do you not agree that there's a point somewhere in between them where the gravity of the two stars would be equal? If you were like a little astronaut floating in space, where would you have to go for the gravity to be equal between the two stars? Anyone think they can answer that? For the gravity to be equal, would you be closer to the white dwarf or closer to the main sequence star?
The white dwarf, right?
Yeah, it might be something like, I don't know, down there somewhere. You know, sometimes stars, when they're in a binary pair, can suddenly go from being normal main sequence stars and they can swell into red giants. And when that happens, their envelopes get so big that they can reach the gravitational equilibrium point between their white dwarf brother and themselves. And take a guess what happens then. Material from one of the stars starts to spill over across the gravitational equilibrium point, and the white dwarf will suck plasma off of the main sequence star and spill it down onto its own companion. This forms a really crazy situation where the gas from one star is being slurped off onto the white dwarf, and the gas starts to spin around and around and around and around into a super hot accretion disk, a disk of hot plasma that gives off X-rays. And sometimes the gas actually falls onto the star and creates little nuclear explosions. This is what is called a nova. Let's take some notes about that. This will be one of our last points for the day. This is a so-called high mass transfer binary. And it's an important stepping stone in the evolution of stars because you'll remember that roughly 50% of all stars are binaries. So here we have a white dwarf, and here we have a main sequence star. And this here is the so-called gravitational equilibrium point, also known as the Roche limit in professional astronomy. At some point, the main star will evolve from a main sequence star into a red giant. And when that happens, its radius will swell to over 100 times its original value, sometimes forcing the star to cross the equilibrium point. When that happens, plasma will in-spiral down onto the white dwarf, and it will form a hot radiating disk called an accretion disk. This accretion disk will spill new material onto the white dwarf. So fresh hydrogen gas spills over from the red giant onto the white dwarf. This creates a little burst of nuclear explosions called a nova. A nova is a white dwarf flare-up due to gamma rays and X-rays being produced from the surface of the star. You know, one of the interesting things about white dwarfs is that because they are held together by degeneracy pressure, if you add more gravity to the star will actually shrink instead of expanding. And the cartoon goes something like this. I thought I had a cartoon of it. Just a second here. In a normal star, somewhere around slide 35, in a normal star, if you add more matter, you add more pressure and more temperature, and that tends to puff the star out. But in the case of a white dwarf, every time you add matter, you add gravity, but the pressure does not increase because the pressure does not depend upon temperature. This causes the white dwarf star to get scrunchier and scrunchier and to collapse. In maybe 1918, there was a famous astronomer, Indian astronomer named Subramanian Chandrasekhar. And yeah, I know, that's a mouthful. Chandrasekhar used the equations of general relativity to predict what would happen to a white dwarf in which you added too much matter to it. He knew that in a normal star, the gases would be bopping around something like this. But in a white dwarf, where the atoms were compact, it was the electron repulsion that prevented the star from collapse. And yet, as you squeeze the star, the velocities of the electrons should get higher and higher. Eventually, his genius was to realize that the star would undergo a catastrophic explosion if the velocity of the electrons would approach the speed of light. And he worked out a mathematical equation called the Chandrasekhar limit. The Chandrasekhar limit was the point at which matter would spill onto the white dwarf, raise the velocity of the atoms to the speed of light, and the star would go through a catastrophic explosion known as a type 1a supernova. And I'd like to show you an example of what a type 1a supernova would look like. We've never seen one inside of our own galaxy, to the best of my knowledge, but we've seen them inside of other galaxies. Now you're looking at a galaxy that is tens of millions of light years away. And this nucleus of the galaxy is not one star, but is probably something like 10 billion solar masses worth of starlight. This dot that you see here is a type 1a supernova that came from the explosion of a 1 solar mass star. The point that I'm trying to make is type 1a supernovas are so brilliant and so violent that their luminosities can rival the collective starlight of 10 billion suns. And you can see white dwarf explosions from hundreds of millions of light years away. This is my final point today. If a white dwarf exceeds a key mass known as the Chandrasekhar mass limit, so this is the absolute upper limit to a white dwarf, it's called the Chandrasekhar mass limit. it will result in a dramatic type 1a supernova. And that's all the time we have before our homework today. Hey, look, guys, before we take our break, a couple of you should really try to participate in the class here. If you guys can think about it from my point of view, today I floated the idea of not having an exam, and I can't help but notice that one student is having a face-to-face interaction with me. Now, I have a pre-recorded lecture from this summer that I could show you guys if you want to just fuck off, right? That's the message I'm getting, is I want to fuck off. So I want to fuck off too, you know? Your lack of enthusiasm is causing a lack of enthusiasm in me. And maybe I could just ping the video your way and I could go and do something that I'm interested in. This has to be a two-way street. I know not everyone is going to share, but a couple of people need to share with me, so I'm not talking to an empty room. That is going to irritate the fucking hell out of me. So some of you are obligated to talk to me. Thank you. Now, not now, but especially during homework. I am not doing this I have this homework pre-recorded. Do you want to know why I'm doing this live with you? For obviously no good effing reason. I don't have to be here. I could just give you I am allowed to give you the pre-recorded lecture, and I could go smoke a joint or whatever people do when they're not teaching, okay? So don't tempt me to do that. I'm here to have some time with you. So I'll see you guys. Take a 15-minute break, and then we're going to crank out this homework, and someone better participate. All right, I'll see you guys then. Okay, time for homework number 11, chapter 18. Sorry, homework number 12. Homework number 12. Okay. Runsack, looks like it's you and me, buddy. I don't know what's wrong with this class today. You guys are usually not like this. Okay, let's get our name. AS1020.
Hey, Professor, I opened up the homework 12 and the thing's upside down.
Oh, bloody hell.
Yeah.
All right, hold on. Let's see what we can do about that. Upside down, you says. Let me verify that's how it looks on my screen. All right. This is easy enough to correct, I believe. Let's go to astronomy 10. Ooh. Homework scans. Chapter 18. Okay, there you guys are. All right. Can I rotate with this? Come on. Pan and zoom. Huh. If I had Acrobat Pro, which I don't have anymore because CCR.
At the top, rotate view.
I'm sorry, where?
Whatever you were just hovering over. Rotate view.
Thank you. Thank you very, very much. Okay. There we go. So let's see if we can save that. File, save as chapter 18, overwrite. Okay, that's good. And now I can edit this. Come on, Blackboard. Get your shit together. All right. All right, I want to remove this. Mark for removal. And then I want to upload. Come on. Hey, chapter 18. All right. Hopefully this all works. Hey, guys, click on that and see if you had any better luck this time. Fudge. Oh, bloody hell. It's still upside down, huh? What did I do wrong? I did
So when
everything.
I opened it, I was able to rotate it in the screen. So I don't know if we can do it.
I don't know if everyone else is going to have that ability / technology.
Oh yeah, it does work. It's top right. There's an arrow where you can rotate it on our side.
All right, I'm sorry.
You're good.
I think it's because I was trying to delete. I think I need to delete it. Let me go back to the file and see what happens here. If I double click this, it's right side up now. Oh. I don't know how that happened. So I should have paused the recording. Oh my God. So you just did that up here? Yeah, just do that. I don't know what the hell is wrong with this stupid thing. Okay, what are our numbers? Fine, I'll look them up because I've got nothing better to do. Hold on, let's see here.
I've got it 52. Hold on one second. 52, 53, 55, 56, and 61. Sorry. Go ahead.
All right, okay. So let's start with chapter 18, number 52. Runsack, you're up.
You got it. Let me know if the music here is too loud.
I can deal.
Okay. 52. A black hole. You've just discovered a new X-ray binary, which we'll call Hype X1. The system Hype X1 contains a bright B2 main sequence star orbiting an unseen companion. The separation of the stars is estimated to be 20 million kilometers, and the orbital period of the visible star is 4 days. And let me know when you're ready for A.
Can you give me those two data, those two givens again?
Yeah. The separation of the stars is estimated to be 20 million kilometers, and the orbital period of the visible star is 4 days.
Okay, hold on. Before we go forward, Runsack, you guys have to draw a picture with me to understand what's going on. We have a B2 main sequence star, and it is in an orbit with an unknown compact degenerate object. This object is too small to give off any detectable visible light, and there are three possibilities as to what it could be. It could be a white dwarf, it could be a neutron star, or it could be a black hole. And our job is to determine which of the three objects it is. Now, there are ranges for the masses of each of these objects. I only got to tell you about the Chandrasekhar mass limit today. if the mass is less than or equal to 1.4 solar masses, your object is a white dwarf. If the mass is greater than 1.4 solar mass units, but it is less than 3 solar mass units, it is a neutron star. And if the mass is greater than 3 solar mass units, it will be a black hole. And these are numbers that you just kind of have to know to solve this problem. I sort of got part of the way through this journey today, but it took a while. Our goal is to use NK3 to find the sum of the two masses, and then to subtract out the B2 star to determine the mass of the unseen companion and thereby determine its nature. Runsack, before you read part A, somewhere in the problem they tell us what the mass of a B2 main sequence star is. What do they give us for that? Maybe 10 solar mass units or something?
Let me go back. You want me to read A?
I want you to read B, actually.
Okay, I'll read it again. Oh, B. Determine the mass of the unseen companion. Is it a neutron star or a black hole? Explain. Hint, a B2 mean sequence star has a mass of about 10 solar masses.
So we know that this one has a mass of 10 solar mass units. Okay, take a moment to write that down because I need to erase this. I'm running out of board space. Okay, I'm going to erase. Arunsak, tell me part A.
All right. Use Newton's version of Kepler's third law to calculate the sum of the masses of the two stars in the system.
I prefer to use the kitty edition. The total mass of the system is a cubed over p squared, where a must be measured in astronomical units and p must be measured in years. Okay, Stacy, help me convert my separation from 20 million kilometers into AU. Dimensional analysis is a U job.
This is the stuff that makes me turn my video off, just saying.
Well, you know what,
I
guys?
get it. No, I get it. All right, I'm sorry.
If you're wimpy and if you're afraid, then you are not going, you're missing the point, right? The point
Right.
is to be forced to interact with me. That's love. That's not torture. You just don't get it from the teacher's side, right? You need to do these uncomfortable things to learn. Do you think you could ever learn how to do? My father was a carpenter, and I used to sit around watching him build. He built us our beds, our bookshelves, so many cool things. And I sat there so many hours as a kid watching him build bookshelves and tables and these beautiful works of art. Do you think I know any carpentry by watching? No, I don't. I don't. You learn those things by doing it. You got to put the hammer in your hand. You got to bang at some nails. You got to miss. You got to do something. You can't just watch. You can't be a troll. You have to participate. Okay, with that said, convert this to AUs, please, Stacy.
All right.
Use your 4 steps of dimensional analysis.
All right. So I'm sorry. I have to go to AUs.
Yes.
So
Runsack's hooking you up with the conversion factor. But there's more to it
Runsack,
than
thank
that.
you. I would really appreciate that. All right, so kilograms. So it would be,
Kilometers.
you know what? I'm honestly just really lost today. I'm sorry. I'm multitasking and it's not working well for me.
Okay, so could you go to the
I need
first
to go
page?
back and review, honestly.
Well, then I think that's a great idea. So why don't we go to the first page of your notes where we have the 4 steps of dimensional analysis, and we're gonna follow our manual, our instruction manual for dimensional analysis.
All right, so we're going to put the KMs on top, or on the bottom, excuse me.
Oh wait, we're gonna make a division bar first, right?
Yes, yes.
All right. So
KM.
KM's on the bottom, and
And we'll go to meters. Can we go to meters?
well, if you check out the conversion factor that Runsack put in the chat, you'll see that he gave it
Runsack.
right from kilometers to AU, right?
Okay, so let's do yeah, AU on the top.
All right. Why try harder when we can try less hard?
I love that. All right, so 1 on top,
Yep.
and so it'd be 150. No. Runsack, help me out.
You had it. It was 150 times 10 to the 6.
150 times 10 to the 6 on the bottom.
It's
Okay.
right there. Yeah. This isn't hard stuff. This is easy. Wow, you guys really don't want to take that final exam. Holy moly. Okay, all right. This is Stacy. You have psyched yourself out. You know how to do dimensional analysis.
I know I do. I
For
know.
God's sakes.
I do know this.
All right, punch them up. What you got?
0.13 AUs.
Christopher, help me convert 4 days to years. Okay, Christopher doesn't want to do it, so Runsack, you could do it.
Please.
I don't think he heard you. That's why.
Oh, I'm here.
Okay.
I can hear you.
Am I still doing it, or is Chris doing it?
I don't give a shit anymore. Just somebody do it.
Okay. X bar.
Yeah.
Days bottom. Years at the top. 365 to 1.
And what do you get?
0.01.
Give me 2 sig figs. That's only 1 sig fig.
0.011.
Years. All right. Let's plug this into the kitty edition of NK3. The total mass of our system is 0.13 AU cubed divided by 0.011 years squared. Punch them up.
$18.2.
Units.
Is it solar mass units?
Excellent. It's certainly not kilograms if it's 2 stars, right? That's the total mass. And that equals the mass of the B2 star plus the mass of the unknown companion. So, class, what is the mass of the unseen companion?
8 solar mass units.
Good. So what's the object then, Christopher?
Black hole.
Exactly. This is too
Rip
massive
star.
to be either a white dwarf or a neutron star. I'm going to try to do a demonstration with our next problem. So believe it or not, guys, today I actually have kind of a lot going on. I have to finish my promotion package by tomorrow, and I promised my father I'd go help him move some furniture from his girlfriend's house. So I'm having a stressful day here. So what I'm going to do is I'm going to do the next problem without any participation for you guys. And I want to demonstrate the difference between you guys doing some work and me doing it all. I actually like doing it all for you. You know why? Because it gets done faster. And time is of the essence for me today. So let's have a demonstration of how number 53 can go. I still want you to read it. So Christopher, can you read us chapter 18, number 53, please?
Yeah, sure. A black hole 2. You've just discovered another new X-ray binary, which we will call whatever. The system contains a bright G2 main sequence star orbiting an unseen companion. The separation of the stars is 12 million kilometers, and the orbital period of the visible star is 5 days.
Okay. So first thing we're going to do is we're going to convert into the Keplerian units. So we'll start with 12 million kilometers. We'll go from kilometers to astronomical units. The conversion is 1 to 150. 12 parts divided by 150 is 0.08 astronomical units. 5 days will convert into years. 1 year is 365 days. Remember, guys, I'm fast. I'm faster than you. That's why it's fun to be me. All right, so 0.014 years. Now we're going to plug this into the Kitty edition of NK3. Is there a part A, Christopher?
Yeah.
All right. So the total mass is 0.08 astronomical units cubed divided by 0.014 years squared. And if we punch those up, we get 0.08 cubed divided by 0.014 squared, and we get 2.6 solar mass units. I know from experience that a G2 main sequence star has a mass of 1 solar mass unit. And I know that because the sun is a G2 star. So for part B, the mass of the unknown companion is 2.6 solar mass units minus 1 solar mass unit, which gives me 1.6 solar masses. What is the nature of my compact object?
It's a neutron star.
Good. And that's the difference between me doing a problem versus you doing a problem. It's faster. I just don't know if it's better. Can I erase? Okay. Chapter 18, number 55, Arunsak Hit me.
Neutron star density. A typical neutron star has a mass of about 1.5 solar masses and a radius of 10 kilometers. Calculate the average density of a neutron star in kilograms per cubic centimeter.
Is this a part A or what?
This is part A. What I just read was part A.
You guys will remember that from today's lecture, we calculated the density of a sphere as 3 times the mass of the object divided by 4 pi r cubed. Here we need to convert to, they give us some units, right? What units do they want?
They want cubic per centimeters.
Wait, cubic per centimeters don't make no sense.
I mean, let me see. Kilograms per cubic centimeter.
Yeah, this is kind of a weird unit system for density. Normally people use grams per cubic centimeter, but they want kilograms per cubic centimeter. We're going to do our conversions right inside the problem because that's allowable. So the mass is 1.5 solar mass units. And you guys will remember that the mass of the sun is 2 times 10 to the 30 kilograms. So I'm going to put the conversion inside the M. I'm also going to put the conversion to centimeters. Divided by 4 times pi. Earlier, Runsack, you asked me if there was a direct conversion from centimeters to kilometers. There is. It's 100,000 or 10 to the 5 centimeters per kilometer. That's got to be cubed. Go ahead and calculate the density for me. That's your job.
I got 7.2 times 10 to the 11.
Excellent. And the units, Christopher?
Well, that would be kilograms per centimeter thingy.
Centimeter cubed. Okay. What's part B, ask a Runsack?
Compare the mass of the 1 centimeters cubed of neutron star material to the mass of Mount Everest, which is approximately 5 times 10 to the 10.
The mass of 1 cubic centimeter of neutron star over the mass of Everest. If it's 7.2 times 10 to the 11 kilograms per cubic centimeter, then 1 cubic centimeter will be 7.2 times 10 to the 11 kilograms. And what do they give us for Everest again?
It's 5 times 10 to the 10.
Okay.
14.4.
And what does the 14 mean, Christopher? Christopher, what's the 14 mean?
Isn't that like a ratio or something?
Okay, so Runsack.
The density of a neutron star is 14 times more denser than Everest.
A 1 centimeter cube is 14 times more massive than Mount Everest. Today I held up a little Mahjong cube, right? And I said that that was worth 2 vans worth of matter if it was a white dwarf. If it's a neutron star, it would be 14 Mount Everests packed into one of those dice, which is pretty wild. 14 times more massive. The reason why what you said at first was not correct, Runsack, is because Mount Everest is made mostly out of granite. And granite has a density of 3 grams per cubic centimeter. So clearly it's way more than 14 times denser. Do you understand? I know we were calculating density, so you got a bit garden pathed, but it's not the same thing. Runsack, let me know when you're good to go.
I'm good.
Okay,
You're
Chris,
good.
can you read me number 56?
Yeah, sure. Schwarzschild radii.
The Schwarzschild radius.
Oh, whatever. Calculate the Schwarz whatever
Of a black
radius
hole.
in kilometers for each of the following.
Okay, next class we'll learn a little bit about black holes. A black hole consists of a singularity, a microscopic dot that contains all the mass, and then there is an invisible region of space around it called the event horizon. The Schwarzschild radius is the radius of the event horizon, of the bubble that protects the black hole. There are 2 formulas for the Schwarzschild radius. If you use MKS units, it's 2 times G times the mass over C squared. There's a shortcut that you can use when the mass is in solar mass units. 3 kilometers times the mass. So let's label it. In this equation, the mass must be in kilograms. In this equation, the mass has to be in solar mass units. Which version that you want to use depends upon how the question is asked. So let's try question A, Christopher.
Okay. A 10⁸ solar mass black hole in the center of a quasar.
This is what's called a supermassive black hole. Which version do you think is better to use in this case, Christopher?
That'd be the version 2.
Yeah, because we've got it in solar mass units. So this should be pretty easy. The Schwarzschild radius, 3 kilometers times 10⁸ solar mass units gives us 3 times 10⁸ kilometers. Okay, Christopher, B.
A 5 solar mass black hole that formed in the supernova of a massive star.
Once again, we're going to want to use the simple version. 3 kilometers times 5 solar masses is a 15 kilometer Schwarzschild radius. Take a moment to jot that down because I'm going to have to erase it. How we doing? I'll erase. Part C.
A mini black hole with the mass of the moon.
The mass of the moon, 7 times 10 to the 22 kilograms. I need to look that up. I think I know what that is, but I'm not sure. Yep, damn, I'm good. I am so good. Chris, what version should we use here?
Version 1.
Yeah, because it's MKS. So the Schwarzschild radius will be 2 times 7 times 10 to the minus 11 with units meters cubed per kilogram per second squared, all times 7 times 10 to the 22 kilograms, divided by the speed of light squared, 3 times 10 to the 8 meters per second squared. I'll just be reading my magazine while you guys do the calculation there. Wow, this article covers many of the topics that we talked about in our class.
I got 1.1 times 10 to the negative 4.
Units?
That'd be like kilo whatever's right, or am I incorrect?
No.
Wait, hold on. This is the radius. Be kilometers?
Kilometers is not MKS.
Meters.
Meters.
Yeah,
How many
okay.
millimeters is that?
Meters.
Are you good at the metric system? How many millimeters?
Okay, so that'd be
How many millimeters are in a meter?
100.
It's 100 centimeters. Millimeters
There's
of
a
the
million millimeters.
what?
1,000 millimeters.
Okay, so
Then you add 3 more zeros. It's 1 times 10 to the 5, 6, 7.
false. -4 plus 3 is -1. You all need work on the metric system, okay? It's 1/10 of a millimeter. That's how big the moon would be. The radius of the moon, if you turned it into a black hole, would be 1/10 of a millimeter. Yeah, Cameron, I'd say a millimeter. I think a BB, like the BB you shoot from a BB gun, I bet that's 2 millimeters. I think I have BBs.
How is that even right with nature? Like, I don't get that. That it can be that small and then just insane.
The idea behind the Schwarzschild radius, I forgot, I haven't looked at these forever. I have BBs. When I was a kid, I loved BB guns, but now they're, well, I'm too old for such things. Let's see. How big is a BB? A BB is roughly 4 millimeters in diameter. So a BB is 2 millimeters in radius. To turn the black hole, to turn the moon into a black hole, you'd have to crush it to smaller than the diameter of a BB. You'd have to crush it to 1/20th the radius of this BB. Isn't that crazy? And if you did that, the moon would become a black hole. It would probably mess up its orbit a little bit. Keep that BB handy, you never know. Okay, what's part D ask? I'm gonna erase this. Well, maybe it would, Cam, maybe it wouldn't. Probably it would. The moon's pretty close. What's part D?
Okay, a mini black hole formed when a super advanced civilization decides to punish you unfairly by squeezing you until you become so small that you disappear inside your own event horizon. Assholes.
So let's say that on a good day, I weigh 180 pounds.
I wish.
Say that?
I wish I weighed that much.
Actually, I think I actually weigh 200. I was wishful thinking. So
Even still.
So that means your mass is about half your weight. So I'm probably 100 kilograms worth of, oh man. Okay, so let's turn this into a black hole using the version 1 of the Schwarzschild radius. 2 times 7 times 10 to the minus 11 meters cubed per kilogram per second times 100 kilograms divided by 3 times 10 to the 8 meters per second squared.
.7 times 10 to the negative 17 meters.
So 5 times 10 to the negative 17 meters. Can Runsack, can you back that up? I need to make sure that someone else is getting that number too. Don't make me do it. That's not fair. To turn the Earth into a black hole, if you plug the Earth's mass in, you'd have to compress it to about a centimeter, which is the size of this ball bearing. I also had a little Earth marble, but I can't find it.
I got something else. Got 1.5 to the negative 25.
I think that's correct. Well, since there are no other human beings interacting with me, I guess I'm going to have to do the calculation to break the tie, which is extremely annoying. A Runsack is correct. A Runsack, should we convert that into some other more reasonable unit? What do you think we should use?
Millimeters. Nano?
Negative 25. Nano is 10 to the minus 9.
So even smaller? I don't know what would be smaller than nano.
Pico? After pico comes, not atto, but deci, centi, milli. Micro is 10 to the minus 6. Nano,
Yocto.
yoctometers, 10 to the minus 24. So how many yoctometers is this?
Like 1.
No, it's 10 to the minus 24. This is smaller than a yoctometer.
It'll be 0.15.
Very good. 0.15 yoctometers. That's how small you would have to be compressed to turn your ass into a black hole.
Wouldn't you like just dissipate at that point?
It is
once
true
that's
that
small.
many black holes have a shorter evaporation scale. Their Hawking radiation will boil away. I'm not sure. This is definitely a mini black hole. So yes, I don't know what the time scale is for Hawking radiation. That's what Stephen Hawking, the guy in the wheelchair, was famous for. He worked out the formula for how long black holes take to evaporate. Hawking radiation. I wonder if they have it here. Black hole evaporation time formula. Well, I was hoping there'd be a simple formula we could look at. Shit. Usually there's a way to. Okay, I need to look it up. I can't remember the formula for the Hawking radiation. In any case, I've got too much to do today to mess around. So let's crank out our last problem, number 61. I'm erasing. Emily, could you read me number 61 since you're in the house now?
Sure, 1 second. I'm just going to pull it up. Challenge problem. A neutron star comes to town. Suppose a neutron star suddenly appeared in your hometown. How thick a layer would Earth form as it wrapped around the neutron star surface? Assume that the layer formed by Earth has the same average density as the neutron star. Hint, consider the mass of Earth to be distributed in a spherical shell over the surface of the neutron star, and then calculate the thickness of such a shell with the same mass as Earth.
This problem
The
sounds.
volume-
Oh,
Go ahead.
before we read that equation, let's draw a picture, okay? So here's our typical neutron star. Our neutron star will have a radius of 10 kilometers. And typically the mass of the neutron star, I think in the previous problem, we got 1.5 solar masses. And you'll remember that the density was it 7 point something times 10 to the 11 kilograms per cubic centimeter?
7.2.
7.2, okay. I'll put the 2 in later. Now, this object is smaller than Earth. It's roughly the size of Boston or New York City. But because it's so much more massive than Earth, Earth would actually stick to the neutron star, and Earth would turn into a thin layer of paste at the surface of the neutron star. So our entire planet would get compressed into a hyper thin shell. All we know about this shell is that the shell was once Earth, so its mass is 6 times 10 to the 24 kilograms. We know that the density has to be the same as the neutron star, 7.2 times 10 to the 11 kilograms per cubic centimeter. And our job is to find delta T, which is the thickness of the neutron star. And they gave us a formula for the volume of a shell, didn't they, Emily? That's what you were about to read to me. What is their equation for the volume of a shell?
Volume of the shell equals 4 pi r squared times the thickness.
And this is kind of interesting. To get the volume of a shell, you basically take the surface area of the star, and since you're only lifting it up by a tiny amount, you just kind of multiply it by that little delta T. Now, the way we're going to approach this is from the point of view of density. I know that the density of the shell is the same as the neutron star, but that the density of the shell is made by taking the mass of Earth and dividing it by the volume of the shell. And all of that has to equal it has to equal 7.2 times 10 to the 11 kilograms per cubic centimeter. I can now substitute in the equation for the volume of a shell to get the mass of Earth divided by 4 times pi. What radius am I using? The radius of the neutron star or the radius of Earth? What R is this R?
The star.
Right, because this is the thing that you're being compressed to, and you're expanding it by a teeny bit. Very good. This is the radius of the neutron star times the delta T, the thickness. And we're trying to solve for the delta T, the thickness of our Earth layer. If we solve for delta T, we get that the thickness will be the mass of Earth divided by 7.2 times 10 to the 11 kilograms per cubic centimeter times 4 times pi times the radius of the neutron star squared. Okay, I'm running out of board space, so I have to go back up. So take a moment to jot that down, and then we'll continue. Okay, erasing. Therefore, the thickness of my shell will be the mass of Earth 6 times 10 to the 24 kilograms divided by 7.2 times 10 to the 11 kilograms per cubic centimeter times 4 times pi. Hey, what's the conversion of Runsack from centimeters to kilometers?
But oh man.
Does anyone remember? Runsack, why don't you use your skills in dimensional analysis and work it out on a piece of paper?
What was it again? Centimeters to what?
Well, we have to multiply by the radius of the neutron star squared here, right? The radius of the neutron star is 10 kilometers, but I can't put in 10 kilometers squared because we've got cubic centimeters. So I need to convert from kilometers to centimeters. So 1 kilometer is equal to how many centimeters? I refuse to move forward and finish this problem until one of you gets me the answer.
Is it? It's 1 to the 100,000.
How do I express that in scientific notation?
1 times 10 to the 5.
Excellent. So in other words, I can just plug in 10 times 10 to the 5 centimeters squared, can't I? I could have made it 1 million, but whatever. Okay, calculate my thickness. This reminds me of a book. Where's that book? Yeah, here it is.
I got 663,145.
Something's not right, Chris.
Yeah, fuck me, buddy.
I think
I got 0.66. The rate?
Okay, yeah, 0.66.
units.
Centimeters.
If Earth were to be pasted onto the surface of a neutron star, the entire planet would be a centimeter thick on the surface of a 10-kilometer sphere. Now, if you'd like to read more about what a hypothetical life on a neutron star might be, I'd like to suggest this totally amazing book by Robert Forward called Dragon's Egg. Dragon's Egg is part of a special genre of science fiction called hard science fiction, where the literary value of the book is subservient to the science, and they're way more interested in making the science real than keeping the book interesting, except the book ends up being wicked interesting. It's a hypothetical future in which an advanced human race discovers a bunch of aliens living on the surface of a neutron star. But you got to get this, guys. Because the aliens are under so much gravitational pressure, the aliens are squashed to be about the size of a chia seed. And for that reason, they are called the Chila. Now, just to show you how weird this book is, oops, I don't want to delete that. Just reading the synopsis on Wikipedia is so hilarious of what happens to the astronomers. A neutron star with a surface gravity 67 billion times of Earth and inhabited by the Chila, intelligent creatures the size of a sesame seed who live, think, and develop 1 million times faster than humans. Why? Because of gravitational time dilation. Like 1 second in deep space is like hundreds of thousands of years for the Chila. So what happens in the book is the human beings come to the surface of the neutron star, and the Chila are in a primitive barbarian state where they're herding salt crystals of neutron goo on the surface, and they've got these little yaks that they pull around the neutrons with. And the humans try to broadcast a message to the Chila and say, hello, aliens, we're human beings, it's nice to meet you. But because of the gravitational time dilation, the 2 or 3 minutes it takes the message to beam to the planet and back takes so many hundreds of thousands of years for the Chila that they develop into a hyper intelligent species. And at the end of the book, they kind of beam a message back, which says, hey, it's nice of you guys to say hello, but you're so stupid now in comparison to us that it would be highly unethical for us to continue this conversation. And then they shut it down. And that's the whole book. It's fucking amazing. So I highly recommend reading Dragon's Egg. It's totally weird. I know, it's so hilarious. That's why hard science fiction is so great. So by the way, I gave a fast synopsis of that, but read the Wikipedia entry. It's so funny that it's almost like reading the book itself. And then if you want, go ahead and buy the book. It's hilarious. Okay, that covers our, yeah, it does sound like a shitpost. Anyways, that covers our homework from today. I got a lot to do, so I'm gonna bounce. And yeah, please don't forget to please upload this homework ASAP. And I will meet you guys on Tuesday. We will decide then, well, next week I'm gonna make a final call about the exam, but I'm leaning towards letting you guys off. But listen, I don't know what happened with today. Some of you participated a little, but you gotta be all in. If we're gonna just have 2 more lectures and I'm letting you off the hook, you gotta participate with me. Don't make me just, yeah, everything hurts from carrying what? Oh yeah,
This lecture.
right, yeah. That's not fair to a Runsack. It's not fair to me. So I don't know if you guys just had a bad day or an off day, but please, some of you hang out so that it makes this more interesting. Okay, so I'll see you guys on Tuesday, okay? Over and out.